Okay, good morning everyone. So welcome to this class. So the class name for this one is Reliability and Value Physics for Semiconductor. So as you have already probably can guess what will be the main content for this class, we will focus on the reliability issues, and not only reliability, we will also focus on how do we understand the value physics here. So that will be the complete focus on the semiconductor reliability. So reliability is one of the key issue for the all kinds of semiconductor device. Probably in this classroom, I believe that you guys working on so many different domains in the semiconductor fields, probably in the logic, in the power, in the RF, in the so on and so on, even in the back end. But all these semiconductor technology requires a very strict reliability spec. So basically, we hope that our device can sustain not only for like the 1 month, 1 year, probably in some of the application, we hope our device can survive for 3 years, 5 years, even for 10 years, if you consider the automotive electronics. So you imagine that you drive a very advanced electrical vehicle car, you just try to buy a new EV from the many brands, but you won't hope that your EV cars will be just got some reliability problem with when you use for the 1 month, 2 months. You probably will hope that your car can be used for more than 5 years, 10 years. And therefore, in the automotive domain, actually we put very strict reliability spec here. So today is an introduction. So introduction, we will briefly talk about how we're going to run this class, and then what will be the content you will be learned. There's some available seats in front. Please come. In the back side, you can come to sit here. Otherwise, you have to stand for 2 hours. Yeah, it's better at least there's some empty space here. So in this class, we will, in today's class, we will mainly talk about for the introduction for this class, how we going to run this class, and what you will expect to learn, and in the end, the most important is how we do the grading, and also how we arrange for the additional student enrollment in this class. Okay, so when we talk about reliability, I think the first most easy one is try to look at the dictionary. So should we learn from the English from the childhood? We always learn from the dictionary to understand the definition. So first one, we have to make clearly what is reliability here. So what is reliability? That's pretty important, because first you have to understand what actually the reliability means here. So we check the dictionary. There's a very famous dictionary called the Merriam-Webster. So if you have already prepared the study abroad, and lots of the English teacher will tell you that you should check the Merriam-Webster, because of course there are many dictionaries around the world, but this one is really classic, and then lots of explanation inside the Merriam-Webster is pretty trustable here. So if we look at the dictionary, and there's two definitions for the reliability. The first one is a quality of state being, the first one is reliable. So for sure, I think the term, since we are try to understand reliability, for sure that we hope one thing or one status that should be reliable. So that's a most important meaning comes from the reliability. And second, for sure, that's the first definition is pretty like the rough. But the second one is getting more important. So when we talk about reliability, that means the extent to which an experiment, test, or measuring procedure yields the same measured results, and also, as importantly, is on the repeat trials. So now we have to understand what does mean the repeat trial. So first of all, we know that the reliability means that it needs to be the status or quality being reliable. And secondly is that when we try to perform the experiment, test, or measurement procedure, and we need to come up with the same results. So that's most important. We need to come up with the same result. But one of the most important things is what we call the repeat trials here. So imagine, I think in this classroom, probably some of you are the fresh student, some of you are currently follow the semiconductor physics, some of you already pretty senior. But anyhow, one of the most important semiconductor device is a MOSFET. So therefore, in this class, we will use a lot of MOSFET as an example to explain the reliability concept. So the MOSFET is a structure. It's a structure that you have this one in the bottom, we have a substrate. And then on top of the MOSFET, one of the most important parts is that we have the source and drain region. So in the left-hand side, usually we call as a source. And the right-hand side is we consider as a drain. And then on top of this source drain, usually we will have the gate dielectric. And one of the most often used gate dielectric is silicon dioxide. For the one who just come in, I think there's some empty space, but probably just one or two. You can count in the first row, I guess. And then probably there's one empty, right? There is also one empty space here. I guess this can be sit for two people. Otherwise, you can count just like this guy. You can sit just on the ground. Otherwise, you have to stand for 2 hours. Okay, so on top of the substrate and source drain, we will usually have the silicon dioxide, and then on top of the silicon dioxide, we have the gate region. And usually we call this as a gate metal. So therefore, if you try to look at from the top to the bottom, so try to look at from the top to the bottom, actually, this device consists of metal on the top, and the second part is the oxide. And the third one is a semiconductor. So this region is a semiconductor. So if you look at from the top to the bottom, it's called the metal oxide semiconductor. And of course, in this transistor, in this device, how do we operate? Is we are going to apply the bias from the drain side. And also, in the meantime, we will apply the bias at the gate side. And in most of the case, actually, we'll ground the source. By the way, as I mentioned, you can come and sit in the ground, just like this guy, for the student who just come in, okay? Otherwise, you have to stay for 2 hours. Of course, we will run a little bit early, finish the class a little bit early today, but it will still take more than 1.5 hours. Okay, so since we were in this device, we will basically bias in the drain side, and also in the meantime, we'll apply the gate voltage. And since we apply the gate voltage in the top metal, so we can imagine that the positive gate bias will start to attract the electrons here. And after a certain moment, we can imagine there's possibly some of the negative electron can be formed under the gate dielectric. The gate dielectric is silicon dioxide is insulator, so usually we expect that the gate voltage applied here can induce a negative electron here because you apply the gate bias, right? So that's a pretty like a high school physics. You apply gate bias from one side, for sure you'll start to attract electrons. And then in the meantime, because we also apply the drain bias in the right-hand side, so we can expect these electrons, negative electrons, can be flow from source to the drain. And therefore, we can start to expect there's some kind of the electron flow from the source region to the drain region. And since this transistor is mainly operate by applying the voltage, which is also related to the electric field, so that's why we call this as a field. Because we apply voltage, voltage is equal to certain correlation with the electric field. So that's why we call this as a field. And this considers how many effective fields that we can apply inside the transistor. So that's why we also call this a field effective. And in the end, this is transistor. So that's why, if you look at the name of this device, it's actually just come from the meaning of first one from device structure. We have a metal, we have an oxide, we have a semiconductor, and because we apply the voltage that's related to the electric field, so that's why we call this as a MOSFET. So in the future, we will only call this transistor as a MOSFET. That's all. So that's why that the MOSFET is considered as one of the most important device that we will use in the daily life here. So if you are following the semiconductor physics device, I think in the end, the most part is you need to understand how is the operation inside the MOSFET here. Of course, this class is mainly lecturing in English. I know probably from you guys, it could be one of the few classes you need to learn from English. But sometimes you will find out that even you look at the Mandarin version of the semiconductor physics, how do they translate the MOSFET? They call this as a 金属氧化物半导体场效电晶体. Basically, I think nobody understands as well. It's just actually the translation of this metal oxide semiconductor field effect transistor. It's just direct translation as a 金属氧化物半导体场效电晶体. So while I was an undergraduate student, I still follow lots of semiconductor classes, and then I try to look at all the Mandarin version textbook. That in the end, I actually got more confused because of in the end, you still need to understand this original English meaning. There's so many original English meaning. If we try to translate in the Mandarin term, it still got confused. Like for example, the BJT. The BJT is what we call the bipolar junction transistor. But if you try to translate in the Chinese, it's called the 双极性接面电晶体. That still doesn't make sense. We still don't understand. So sometimes I would suggest that you guys just you need to get used to the English term, and you need to try your best to. You don't have to speak very fluently in the English, but you need to know at least how to write English mail, and sometimes you need to know how to listen the English. I think that's one of the important. As you also know that our country, Taiwan, is a very small country in the world, and luckily we have a semiconductor right now. So all of our international students here are very interested in the semiconductor field in Taiwan. And you know, but you also know that our big semiconductor company in Taiwan, their main customer is located in the outside. It's not their customer. It's not a Taiwanese company. Their customer are the USA company, Japan company, European company. So anyhow, in the future, you still need to get used to how to talk, or even how to listen, how to write, or how to communicate with a foreigner by using English. But if you need to prepare after you get a job for several years, sometimes too late, because as you know, after you being the age increase to a certain moment, actually your learning capability will start to a little bit saturate. But because everyone is getting older, once you're getting older, you can think very fast. You cannot remember everything. So sometimes your learning capability will become saturated. So, but at this moment, you guys are still the graduate students. So students are the one that who has less pressure. Of course, you guys under the pressure of the thesis, master thesis, PhD thesis. But actually, to be honest, you guys still need to focus on the one thing at this moment, because the main responsibility for you guys now is just taking the course, doing the thesis. And still, I think that's it's relevant, simple task. So it's a good moment. You should start to get used to the English environment, especially in the NYCU. I think right now we have lots of international students. It's good, like you can make some international friends here. That's also one of the key importance. Okay, so back to the class. So now we introduce the basic structure of the MOSFET. And next one is we need to understand what would be the typical characteristic for the MOSFET here. And to be honest, it's not that difficult. So since right now you try to apply the drain bias in the VD at the drain side. So now usually we are very interested in the current in the drain side. So we are also very interested in the current from the drain side. So therefore, if you look at all the no matter for the literature, for the paper or textbook, the most important characteristic for the transistor is drain current. That's what we call the ID versus our gate voltage. That's most important electrical characteristic we are looking at. So that's an IDVG graph here. So if you try to look at this characteristic, and you can imagine, this is a graph that we try to consider. We apply the gate bias on the gate side, and we try to sense the current from the drain side here. So therefore, the typical characteristic for the IDVG curve is that the first one, you will slowly increase the gate voltage. After a certain moment, you start to attract enough electron. You start to make the channel being inverted with electron. So therefore, you start to see the current increase here. So first one will slowly increase our gate bias. At a certain moment, you will start to have enough electrons here. And because at the meantime, the drain bias is constant applied. So usually in this graph, we will apply the VD, for example, 1 volt here. So therefore, the drain bias is constant applied on the drain side. And then in the meantime, you start to gradually increase the gate voltage. So after a certain moment, you start to have enough electrons under the dielectric. And because we also apply the drain bias, so now we can expect the electron can start to flow from the source to the drain side. Therefore, that's why we have the drain current here. So, and usually we define this turn on voltage is how we call as a threshold voltage, VTH here. So just let me say again. So this is a typical MOSFET structure. We will only consider to apply the bias in the gate region and also in the drain region. And to simplify the case, first one, we consider the constant drain bias, just like here. And therefore, we are interested in the current ID versus the gate voltage here. So we are interested in this correlation. So we start to gradually increase at the gate bias. After a certain moment, the electrons under the gate region, that's already high enough. So we start to can form the channel. We start to have enough electron that allow us from a flow from source to the drain side. Imagine what I draw here is the electron current. I prefer to draw the electron current, but as you know, the current is in the opposite way of the electron current. So the way typical we consider current is in this way. But actually, that's just a definition. The definition of the current is the opposite way of the electron current. But here, the electron is a major carrier, so that's why I prefer to consider the electron current. So electron current is flow from the source to the drain side. So therefore, we have this beautiful curve as shown here. So if you can try to follow up, if you can try to understand this one, if you can understand the IDVG curve, actually you basically almost complete the semiconductor physics device. I would say like more than 50%, because 50% of the semiconductor physics device is major trying to telling us that why the IDVG curve here. In this class, we will use a lot of the MOSFET as an example because the reliability is not the theoretical class. It's pretty practical. You need to combine the real device phenomenon here. So that's up to now. This is something we will learn from semiconductor physics device. For sure, in this class, we will not stop here. But what we are actually interested in the reliability is this term, repeat trials. Repeat trials, that means you will operate this device 1 time, 10 times, 100 times, 1,000 times, like more than 1,000 times. That means if we try to operate this device for 1,000 times, we hope the device should have the same characteristic. So that's a drain current versus a gate voltage here. So ideally, in the device that we haven't operating, that's we typically call as a fresh device. So that's our fresh curve. That's our fresh curve. But unfortunately, many devices suffer the reliability issue. So if you try to, especially the device that you are fabricate in the university. There are so many reliability issues, so many instability. You should consider that's normal. When I was a student, that's how lots of us are so afraid to see these phenomena because they are afraid to deal with this situation. But actually, you should consider that reliability is a part of a normal. Instability is a part of normal in the device, semiconductor device. So that means once you have a flat device, you operate 1,000 times. It's very often to see the curve will start to shift to the right-hand side, just like here. And then we can see our threshold voltage is increased and our drain current is decreased. So that's the reliability issue. See, so and then let's back to our definition. So definition is mean the extent to which an experiment has or measurement procedure. So we operate for 1,000 times. That's kind of experiment test or measurement procedure. But if this is good reliability, that means we should come up with the same result no matter how many times you operate. But unfortunately, in most of the cases, in our real semiconductor world, we are often to see this is fresh device, and then you operate 1,000 times, you see the threshold voltage increase, you see the drain current decrease. That's the reliability issue, and that's the content in this class that we need to learn how to evaluate this reliability, how to do the testing, and most important, how do we understand the value physics? Why the threshold voltage will shift in the right-hand side? Why the current will decrease? And once we understand, finally, we are possibly to come up with a solution. In the end, we need to do some solution to make sure that once we operate for 1,000 times, your curve will always the same like the fresh one here. So that's the meaning of this reliability. That means we will do the testing for not only 1 time, 10 times, we do 1,000 times, even beyond. And then ideally, you hope all of our results are the same here. And another aspect is, again, if you try to look at the IDVG curve here, so ideally, we have the fresh curve showing the characteristic like here. That's a beautiful curve here. And then we can define our threshold voltage as shown here. But the operation for the repeat trial, that also means that there's a time-dependent characteristic. Because when we operate the 1,000 times, that probably is already equal to 1,000 hours. So you probably operate your device 1 hour per time. You probably operate a device 2 hours per time. So if you operate for 1,000 times, that's probably equal to a certain amount of time. So therefore, we have to focus on the time dependent. One thing between the conventional semiconductor device class and then the reliability is that we need to incorporate the time factor inside. So once we consider all of the current voltage, threshold voltage of state breakdown, whatever, we always need to consider time-dependent factor here. So that's the key for reliability, because reliability is related to the not good as right now. We hope it can be good for 1 year, 2 years, even for 5 years, even for 10 years. And therefore, we have to keep in mind the time-dependent characteristic in the reliability is one of the most important factors here. So the operation for the 1,000 times can be like the 1,000 hours. So we can expect after 1,000 hours, this is a curve. After 1,000 hours operation here, and therefore we will see there's a new threshold voltage here is being shifted to the right, and then the current is degrade here, and therefore we can typically make the graph as try to correlate the characteristic we are interested in this graph. The threshold voltage is the most important one versus the time, right? Because as I say, the most important for reliability is the time dependent. So we were definitely interested in try to plot the key parameter versus the time here. So in the x-axis can be 1 hour, 2 hour, 1,000 hours here. And then ideally, if the device didn't show any reliability issue, we should expect the curve like here, where no matter how long we operate, our threshold voltage is always being constant. And that actually is a perfect case to show that the device didn't suffer the reliability issue. But unfortunately, this is not possible. Every device has a reliability, just related to how large they shift. Some of the shift is small enough that we can accept. So if you put up in most of the case, we can see our threshold voltage is shift increase as the operation time increase here. So that's it's a reliability challenge, and therefore we need to understand why the threshold voltage is shift with respect to time. And second is how do we do the modeling? So if we can come up with a model to model this curve, and then in the end we can extrapolate the lifetime. So we will talk about lifetime later here. So in anyhow, if we see the threshold voltage shift, we see the current degradation. We always call this as a very specific term we usually call in the reliability is how we call the degradations. So as long as we have the characteristic change, that means we have a degradation in our semiconductor device here. If you cannot take the note immediately, it's fine. I think in this class, some of the students is already been following my class before. So I always upload all the lectures in the YouTube, and also I will upload all the notes in the online communication platform like E3 or whatever here. So you can always take a note later. By the way, if you would like to interested to preview, some of you might work very hard, study very hard. If you are interested in preview the course content, actually you can just watch the last year lecture video. That's already, I put it online every year, so you can already watch. I would say the majority content around like the 7 to 80%, probably more than less the same, but sometimes one explanation in the class might a little bit different. Okay, so that's the first definition about reliability. The second part is related to what is a value physics. So still, we were interested to look at some of the basic definitions, so we can check the Wikipedia to understand what is a value physics. So basically, the value physics is a leverage the knowledge and understanding of the process and mechanism that induce value and in the end to predict reliability and also improve the product performance. So now you can see the major important conclusion from the value physics is we need to predict reliability. So once we know why our device will have the threshold voltage shift, why our device will have the current degradation, and then once we understand why, we are possibly to predict reliability and also to improve the product performance. So the reliability is definitely related to, in the end, the product's performance. So that's always the goal is to improve the product reliability and also the product performance here. So again, we can use the previous example to illustrate how we are important to understand the physics in the end to improve a product performance. So in the previous slide, we have been already talked about one of the key reliability key factor we are interested in is the threshold voltage. So we consider the threshold voltage shift versus the time here. And then we are actually interested in the time, not only for 1 hour, 10 hour, 1,000 hour, 3,000 hour, but actually in the real practical semiconductor product, we expect the lifetime can be up to 10 years for a certain product. For example, the automotive car. So you can imagine I believe that right now your parents or your grandfather still drive his 50 years old car. But the 50 years old car, that means there are still so many components inside this 50 years old car that still survive and still being reliable. So that's why when we talk about the automotive, we always put the very strict reliability spec, and we have to predict the lifetime beyond the 10 years here. So as I say, previously we have been already shown the threshold voltage can be increased. The threshold voltage is gradually shift to the right. That means our delta VTH is increased. But the problem is, if you look at the previous slide, if we can test for 1,000 hours, that's already very long duration. So in the lab, in the semiconductor testing facility, 1,000 hours or sometimes 3,000 hours is already the maximum duration that we can test. But how do we guarantee for 10 years? You cannot possibly to test one chip for 10 years, right? Because after 10 years, everything is changed. Besides, you probably were getting older, and then also the product is no longer attractive in the market anymore. So definitely, we are not possible to do the 10 years reliability testing. So maximum duration we can test is around 1,000 to 3,000 hours. So therefore, what we need to do is we first understand the physics, and the next one we have to do the reliability prediction. So what does mean prediction? Prediction means that we come up with a certain model that can help us to extrapolate the time that we are interested in for this product use here. So this is a reliability prediction based on the math and physics. Based on the math and physics here. Just one reminder, since there's still some new student come in. So if you don't mind, you can sit on the ground, just like here. There's one example there. There's one example student sitting. So if you don't mind, you can sit on the ground. That can probably make you more comfortable. Otherwise, you have to stand for a little bit longer time, yes. And so one of the key important is we do the testing up to the 1,000 hours. But in the end, we have to do the reliability prediction. But how do we develop this prediction model? It's based on our math and physics. That's why we need to understand the value physics here. And of course, our goal is always want to make sure that in the end, after 10 years, the threshold voltage is still possibly in the spec that we can accept. In lots of cases, probably the spec is less than certain voltage. For example, less than 0.5 volt. So that's the spec here. So once we do the testing, we can start to do the 1,000 hours, and then we can start to extrapolate the threshold voltage. And afterwards, we will combine all the physics we know, all the mathematics we know, start to do the reliability prediction. In the end, we have to make sure that the 10 years should be smaller inside the spec. For example, in this case, the spec is 0.5 volt here. So if we can make sure that after 10 years, the threshold voltage should be below 0.5 volt, usually we can consider this product is being qualified. So that means this device can start to make the real product, and the customer will buy it because the customer will trust this device reliability here. So that's first things related to predict reliability. But of course, in the end, we still need to try our best to improve the product performance and reliability. So therefore, our goal is still try to improve the reliability as possible as we can. And then if we can make sure this chip is pretty smaller as possible, and then that actually can certainly improve the reliability here. So therefore, we need to start to consider to improve the process. And improve the design. So that's why the reliability is just not about the testing. In the end, it's about the semiconductor physics process, because in the end, we have to use all of what we know related to what kind of process, what kind of the design, in the end, possibly to improve this reliability. So that's, in the end, it's a goal. Okay, so finally, we just finished the basic introduction of what does mean the reliability, what does mean the value physics. Now we will start to try to look at what's the goal in this class. So reliability is, after all, engineering in most practical. So practical, that means 实际. So that's this is the statement come from the former U.S. Secretary of State of Defense, just 美国的国防部长. So in anyhow, reliability is considered is most, if you consider engineering, is the most practical form, because of it's not related to the pure related to the theoretical, pure related to the design, because we need to make sure that the reliability should be in the spec, and then once we use this product, we won't face any issues here. And on the other hand, reliability is an essential part of the successful semiconductor product because it is related to the trust. If we have a good reliability, that's almost equal to we have very great customer trust. So, because you can imagine that if you try to buy the product, in the later slide we will show some of the example. If you buy the product and you use for 1 month, 2 months, you got a problem, you will start to feel not good about, you will lose the trust for this product. So one of the example can be, for example, this is the several years ago, that's already happened a while, that's been happening in 2015 or 2016. That's some of the cell phone, because due to the battery, they start to explode, and then this exploding actually will cause huge damage, not only for the human being, you can damage your life, but also you can damage all the consumer electronics nearby. So basically, no reliability is equal to no business. That's very important. So far we have so many examples relating. So recently, if you look at if you pay attention to the electrical vehicle industry and the electrical vehicle news, so you probably heard about that probably last month, that the battery, inside the electric vehicle car, the button is the huge battery, the battery to drive our EV. And then last year in the South Korea, the lots of the EV car from the Mercedes-Benz is actually exploding in the underground, the parking space, and that's damaged around like the 1,000 of the cars nearby. And of course, I will not, if you look at the news, you will find out that why, because they say all these batteries come from the son of the supplier. So that's actually start to make the Mercedes-Benz so worried, because they are afraid that the customer won't start to buy their EV car. Right now, the EV car is in the very competitive market. So anyhow, if we don't make the device with a good reliability, that actually, in the end, we will hurt our customer trust here. So one of another example is you try to buy the cell phone. There's some very high-end phone, probably from the Apple. It's actually very expensive right now. I think right now the latest phone will come out in the next month. Probably will cost around like $40K for the one cell phone. That's almost equal to one computer. And there's some more inexpensive phone, probably cost like the $10K. But if you want to, the reason why the Apple's product can sell the high price is not only because they have good performance, but sometimes because they have a good reliability. So I saw the news a couple of years ago. There's one guy who traveled in the North Europe, probably like in the very cold region. He suddenly just his iPhone just fall down in the ice. And after 5 years, somebody just found it back, and then the phone is still functional. Once they fully charge, you can still open the phone, and all the image, all the figures, all of the function, all of the memory inside the phone still being acceptable. So that's why this brand, they can sell in a high price. But if you buy some inexpensive phone, probably after 1 or 2 years, you need to change another one. So that's why the reliability is also equal to the customer trust. If you lose the reliability, you actually cannot make a good business in the market. So this is another example. So right now in our electrical vehicle car, there are so many electronics components inside. So we need to make sure that these electronic components are reliable. Otherwise, this not only damage the car, but also sometimes can be damage your life as well. So this is a slide from the Volkswagen, the German automotive manufacturer. So he makes a comparison between the reliability aspect from the consumer versus the automotive here. So in the left-hand side is the typical consumer electronics that we use for the cell phone, iPad, or laptop as well. So in the case of the consumer, actually the temperature range we expect, is around just 0 Celsius degree for 40 Celsius degree. So I think that's a pretty, makes sense. So you won't, that's a typical like a temperature around the earth here. So usually once we need to test the device, the consumer electronic reliability, we will only test in this temperature. And then lifetime is only 1 to 3 years. So you can expect that once you purchase a new phone, you probably can use, I think maximum 4 years is already proved that this cell phone is good enough. Sometimes you can use 5 years. But actually the manufacturer, they actually don't want you use for so long, because then you will never purchase a new phone. So they will try to set like after use 3 years, 4 years, your cell phone start to getting slowed down, and you start to feel like it's getting not functional at a certain moment. There's one joke like every time before the Apple new product release, like 1 month, 2 months before, you will probably feel like your iPhone start to get stuck, will be cracked, and then you even cannot use functional. Of course, this is just a joke. There's no scientific proof, but this also makes like to people realize that actually the consumer electronic, in terms of reliability inside the consumer electronics, of course reliability is important, but the manufacturer also doesn't want your device that can use for too long. Otherwise, they cannot make money. Okay, so we don't have to consider the vibration, there's no acceleration, and then regarding for ESD safety, it's up to A. We will also talk about ESD in this class later. So anyhow, every component has to be verified with the ESD safety. So in the consumer electronics, up to 8 kV for the ESD safety. And then another is acceptable field values is around like less than 10%. So I think it's pretty common that you probably unlucky to buy a new phone, but after 1 week, 2 weeks, you feel like there's some problem. But it's fine. You can easily to find the store. You come back to the store, they will provide you for the new one. So you can imagine when these manufacturer people, they try to make the cell phone, they already expect there's around less than 10% of the value, but they can immediately provide a new one for you. That's no problem. And there's no very clearly for the value documents, and most important, there's no long-term supply. So the long-term supply, that means that if you have a phone that you have used for 10 years, but if you go to the store, you say you want to replace a component, that's not possible. All the store people will just tell you that you should just change the new phone rather than fix it, because there's no long-term supply for the component here. But however, if you look at for the automotive business, that's a complete different scenario. First one, for the temperature range, we need to guarantee the car can be driven safely in all kind of the environment here. So usually the temperature range to be qualified, the semiconductor device, is pretty wider compared to the consumer. Is from the minus 40 Celsius degree up to 165 because that's a typical, like the temperature range possibly around the Earth, because you can possibly drive, of course, you can drive in the normal temperature, but you can also possibly drive in the mid-noon, in the desert region, or in some very cold region. So we have to consider all of the spec and to make sure that our automotive are all functional. And also another aspect is lifetime. Consider lifetime for the automotive actually is pretty longer, because I believe everyone actually is not that rich can replace your car every 5 years to buy a new car. I think that's not possible for everyone. So usually once we buy a car, we expect to drive a car for more than 10 years, and sometimes even for more than 15 years. And then if you talk to your grandfather, probably they have the car driving for more than 30 or 40 years. So therefore, we have to make sure the automotive, the electronics inside the automotive also can survive with such long durations here. And once we're driving, we also need to consider there's a possibility for the vibration, and also there's an acceleration during the driving. And also the ESD safety is higher, is up to 15 kV. And then most important is that the failure rate. Actually, the goal for the automotive is to have the zero failure. Because that's related to the customer trust. If you buy the new car, you spend like several million, you buy the BMW, buy the Mercedes-Benz, but after you drive 1 month, you found that there's something infunctional. You probably will feel very sad, you feel very upset, you feel angry, and then you go back to the car store, they help you to fix, and then after you drive another month, you still found that there's something problem. You probably will lose the trust for this car anymore. You probably won't buy the Mercedes-Benz car because you feel so sick of every month you have to go back and to replace, because of the car is not related to consumer electronics. It's a complete different scenario. In the cell phone industry, you can accept after 1 month your cell phone got broken, you back to the car, they help you fix it with in the 30 minutes, and you still feel like fine. But in the car, it's completely different. You won't hope that the very often failure will happen in the car that you just recently purchased here. So when the automotive industry or manufacturer, when they try to produce a car, their goal is to have the zero failures. Another important difference is a long-term supply. So right now, if you drive, that's up to 30 years. So right now, if you drive your parents' car, probably have been already on the road for 20 years, back to the car still, they still can help you fix it. They can still order the component. If you drive like 50 years old car, 60 years old, there's some very classic, for example, like a Porsche 911 or whatever, you still drive the store and they can help you to fix it. Even the car has been already on the road for more than 50 years. So when we talk about the reliability in the automotive in terms of long-term supply, actually, they already prepare. They can provide for long-term supply for the 30 years. So this is interesting, the table between the consumer electronics and automotive, and you can start to realize that if you look at the different product, actually it will come out with a different reliability spec. So if you back to our one of the genius guys in the Chinese industries called Confucius,孔子. Actually, he also talked about one thing. He said, a man who lacks reliability is utterly useless. Once we translate Mandarin, 就是如果一个 一个人他没有这个可靠的肩膀的感觉，他就是一个没有用的人。But actually what he means here is the same if we replace a man with a semiconductor technology. So therefore, once we try to make the new product, I think in this classroom, every of you is trying to making the new advanced semiconductor technology here. So once we make the product, we deliver this technology to the company. What they care is not only the performance, but sometimes it's also they care a lot about reliability. But unfortunately, it's always there's a trade-off between the performance and reliability. Performance, that means, for example, how large the current for this device, the threshold voltage. Sometimes we also care the subthreshold swing, and also the breakdown voltage, and so on. These are typical performance metrics that we are interested in. But if you only try to fabricate a device that you want to make the best-in-class performance, sometimes you will lose your reliability, because reliability has a trade-off of the performance. If you want to make a device with a good reliability, sometimes you have to compromise performance. You cannot make the breakdown voltage such high, you cannot make the current such high, because all this can also induce some of the reliability issues. And when we talk about reliability, the question we have to keep in mind is that how long of our device for being stable. So that's a key issue. So we always have to, right now, I think you guys are trying to fabricate all about the amazing semiconductor device in the lab, and then of course probably your thesis is just purely focused on the performance, try to make the current as high as possible, the breakdown voltage as high as possible, or the subthreshold swing as low as possible. But you have to keep in mind that once you go to the industry, sometimes we are not only chase the performance, we need to find the balance between the reliability and also the performance. Okay, and then right now I would like to share that how actually the industry people try to make the product from the ideas. So this is a typical timeline for every, not only for semiconductor, for all of the new product around the world. So the first one for sure is our star. So when we try to make a new product, we always got some good ideas in the beginning. But actually, before the ideas, we have to first to understand the requirement. What actually these requirement and the definitions. So, for example, in your thesis, probably, your professor will ask you to fabricate, for example, 1,000 volts of gallium nitride, 1,000 volts of silicon carbide, or the large memory window for a certain memory technology, and so on, so on. So first, of course, we need to set a goal, and that's a requirement definition. And once we have a requirement, we start to brainstorm certain of the concept that can possibly achieve this requirement. So in the end, you probably will come out with like the 5 different concepts. So you come up with 5 different concepts. So this is at the moment of the concept generation. And then we will start to do more research. We'll start to do more research because we want to eliminate some of the useless concepts. So you will start to do the research for concept eliminations. Because you probably come up with a 5 concept, but after we're doing the research for a while, you will realize that there's only like 1 concept. It's doable. It's doable. It means that it can be possibly implemented in the university with limited resource. So that's why we need to remove the other 4 non-practical concepts. So we will do some research. And then we will start to try to make sure our concept can gradually mature. So this is a moment for the maturing. So that's you will start to do more progress, start to make sure that that concept can be worked. And after a while, you will start to have the technology qualification. So you want to make sure that whether the technology you are working on finally can reach our spec, can reach our target or not. So that's a qualification, technology qualification. So this is generally considered the phase for the R&D. So that's actually the most of you guys actually working on in this field, in this phase in the university level. So we start to make some of the requirement to understand what kind of spec for the technology we want to develop. We will come up with several different concepts, and after being a while, we will start to remove certain concepts that cannot be possibly implemented. And then in the end, we will do some progress to start to mature our technology. And finally, we will do the qualification of our technology to make sure that our technology can reach our spec or not. And afterwards, we start to have the product level development. So if our technology is being qualified to reach the spec, and therefore we will start to try to make this as a product. And then also we have the product qualification. And of course, before the product qualification, usually we have the one is called finalize. So we will finalize the detail for everything related to our product. So that's it's a general, like from idea to a product. First one, we do the requirement definition. We start to generate several concepts, and we'll research to eliminate some useless concept, and we start to do the progress to mature our product. In the end, we reach our technology qualification. So that's related to the research and development phase. And once we finish the R&D phase, we start to move to the product level development, and we finalize our product. In the end, we move to the product qualification. But in this research, in this from ideas to product, there's still some missing. Is we have to be careful. So during our R&D phase, it's already important to consider reliability issue. Otherwise, if you look at this timeline, actually none of this is reliability. So if you try to release your product, and probably your product will got some reliable issues here. So to avoid the reliability issues here, so we already have to integrate the reliability testing analysis during the R&D phase. So first one, usually once we do the concept generation, we will consider the preliminary reliability. So we will start to do the preliminary reliability research or study here. So that means once you consider preliminary reliability study here, the concept that you want to remain, that's already exclude the concept that probably can show the instability issues here. So this is crucial to guarantee during your R&D phase, you already take into account the reliability issues here. And also in the end, before the product release, we definitely will do the product level reliability evaluation again. To make sure the product we develop can reach the certain reliability goal. For example, 3 years, 5 years, 10 years, and so on and so on. Before we take a break, of course we will still some, but I would like to announce first, because probably during the break, some of you already will pass by, related to how this course for teaching and learning, and how do we do the additional enrollment. So I want to use this one to quickly go through. First, so first one is intended learning outcome. So this course is basically designed by consider the constructive alignment as shown in here. So we will talk about this detail, but just quickly give you the ideas as to what you expect to learn by the end of this class. So by the end of this class, you should be able to, first one, you can explain the basic operation principle fabrication for the MOS type semiconductor technology. So we will use a lot of MOSFET as an example to understand reliability issue. Of course, in this classroom, probably you are not everyone working on the MOSFET, but lots of the reliability concept can easily extend to the other field as well, as long as you are familiar with the MOSFET. And second one, the important is we will apply the basic statistic and statistic tool for reliability analysis. That's an important part. So this is only the content you will be learned in this class. In the other class, you have been already well learned. For example, semiconductor physics, semiconductor device, semiconductor process, whatever you will learn. But if once we need to do the reliability analysis, we also need to have some mathematical tool. And then in this mathematical tool, the most important part is the statistics. So for sure, you guys have been already learned the statistics, I believe, for the high school. That's pretty normal for everyone. But after I went to the college, actually we will not use the statistic very often because for most of the engineering study, it's less often being used for statistics. But in here, we will still review some statistics because the statistic can allow us to do the lifetime extrapolation, allow us to do the sum of the predictions. And then the third one is for sure, we'll talk about the failure physics of the reliability issues here. So in this class, we also will talk about the most 4 important reliability issues. The first one is a bias temperature instability in the interface trap. And second one is a time-dependent dielectric breakdown. A third one is a mass in transport-induced value. And the last one is the ESD issue. So in this class, we will also talk about these 4 very specific reliability issues. But these 4 are the most important reliability issues. If you work in all kinds of semiconductor device, you definitely will face these issues, no matter from front end, back end, even the circuit level. So therefore, you have to understand. And also, we will have this is first one. So you need to, by the end of this class, we will have divide everyone in a small group. We will do the group presentation. So you need to present the reliability issue using your own words here. So we will talk about this later. And also last one is for sure, not only to understand reliability, but also in the end to design the reliability. We want to design the semiconductor technology. In the end, we hope to design the technology for the long-term stability. So our teaching and learning activities here, so we will use part of 50% will be referred to this textbook, but not all of them, just only 50%. And you can easily find this textbook in the library. So I think they can be downloaded from library. And of course, we will have a course slide and some video. And also there's a topic-based literature that includes a group presentation and group discussion presentation. And you are feel free to contact me if you have any question. We have the two TA for this class, but if in the class with such scale, probably I need to find 1 or 2 TA more here. So, but right now we have the 2 TA. One is Pei Rong and one is Yu Jie. Yu Jie is here. Yeah. And also in this class, because of I prefer to have the much more convenient communication, especially related to the videos and also the slide upload. So I create this group or this one. So you need to add this one. And then afterwards, all the lecture slide I will only upload the lecture slide. And videos. And also the Q&A. If you have any question, you feel free to. And also some of the important announcement that will be only communicate in this Facebook. And another thing, yes, because I want to make an announcement here. So if you feel like this class is suitable you, if you feel like the class is not suitable you, probably you don't have to. You can leave earlier. So first of all, another thing is that our class is original plan in this classroom for sure from 9 to 12. That's 150 minutes in total. But 9 is probably very early for me and also very early for you guys. So therefore, I know everyone, so I have a difficult, especially it's a Monday morning. Yeah, Monday morning is a class like the 9. Sometimes it's very nightmare. So I propose we shift to the 9:30. And then we don't need to have because in the original course schedule, there's a 2 break. But in my class, we have a 1 break in between, like 11 to 11:30, 11 to 11:10. But you feel free to, if you want to go to the washroom, feel free. You want to sleep, whatever you've done, it's all fine with me. You want to eat breakfast, that's fine with me. I'm not sure in this room, I think we can eat something, right? I'm not sure. We have to check the room. But anyhow, you feel free to go to the washroom anytime in the classroom. And then so we will have a class from 9:30 up to the 12:10. And then after 12:10, that will be a Q&A. So if you have any problem with this time schedule, you can let me know. But I have been running this since I joined the NCTU NYCU, so that's already 7 years, 8 years. So I think everyone is pretty happy that they don't have to wake up early. Yes. Okay, so we have the homework. We have sometimes we have in-class assignment, but that's just help you to understand what would be the typical question in the final exam, so you don't have to worry. But most important is we have the group presentation. Yes, I forgot to remove this one because in the past we do have some lab demo session, but that was in the past with a student less than 30. So right now I think we have a student more than 17, 18. It's very difficult. But let's see what else we can do. Okay, so yes, the most important for you guys is about the grading policy. So we have the one oral presentation based on the selected topic. So that will become for 35%. And we only have one exam. It's a final open book written exam. That's account for, again, for 35% as well. And we have homework. We have the attendance also around 50% and 50%. So some of you have been already followed my semiconductor physics device before, so you know in the final exam I always prefer to run the open book. But just a soft reminder that open book is then sometimes you can bring whatever you want. In the lab you can check. Some of the students here has already followed my class in the last semester. Basically in the open book exam you can bring whatever you want. Laptop, cell phone, whatever, course material, slide. But sometimes my reminder is that the more things you bring, the more confused you will get. You will waste so many times try to look at the materials, and in the end you will be very difficult to finish the question. So we will discuss the open book. Sometimes open book exam, it doesn't mean it's easy one. In the last semester, I run the semiconductor physics device, and in the end, the average score for the final open book exam is lower than the midterm. The midterm is a closed book exam, so it's just but it's fine. Everyone still pass. Don't worry about that. As long as you work hard, still should be no problem. Yeah, and then for the oral presentation is need to be delivered by English, but just try to give everyone has a chance to practice, because you should recognize that in the future, I think nowadays Taiwan is considered try to move to the bilingual nation. That means English is going to be our another national language soon, and so just don't worry, just practice. You can practice at home, so don't worry. In the last 7 years, every group they always make a nice English presentation. So I believe the past student can make it. You should be able to make it as well. Yes. So regarding for presentation, we have the four topics. So these are the 4 topics. Basically, I will make the lecture class about 1 or 2 classes, roughly around 2 hours to 3 hours to explain each topic. So include the BTI, TTB, mass transport induced values, and ESD, and then we will assign each topic for one group. And usually when we do the group presentation, the student from one group is randomly selected for the presentation, and then presenter is randomly changed. We'll talk about this later. Don't worry, just some of the small trick that I want to make sure that everyone can contribute the group presentation, not only the one hero person try to take over, and then in the end it's only this hero person's contribution. Yeah, but don't worry, we will talk about this. And by the way, I will help to make the group, so you don't have to find the good friends by yourself. So because some of you probably is new, you don't have friends probably at this moment. Yes, but don't worry. So some of you might be a little bit age 边缘, yes, but it's fine. I will try to find a good friends for you. Yes, that's the most important. That's ideally I set for 40 students, but now it's getting more for 40. So of course we cannot accommodate every person in this class, but I still make some of the additional student enrollment. So first one, you sign up this one, and then there's some question you need to reply. What's your name, university, college, you are graduate or undergraduate, your student ID, your email, and especially explain why you are interested in this class, and tell me why this class will be important for you. So the deadline, so I only allow the additional enrollment to, in the case student who finish this the Google Sheet, Google questionnaire, to finish this Google question by the 12th in today. So after 12, we won't accept any additional requests, because otherwise there are too many students. So that's why the student who come in the first class, they got some, and the student who still stay right now, they have the privilege to sign up this one. Okay, so we will take a break for 10 minutes and we'll come back for 10 minutes later. And if you have any question, just let me know.
周五还有一门另外一门课也是在讲元件可靠度。
对。
那我想问这2门课，
这我没办法comment，我也没上过那门课。对，我没上过那门课，所以我不知道那个老师教的是怎么样。但我只能说，我是用我自己的方法教。对，如果你可以上网看去年课程，你可以大概 roughly 知道。谢谢。
Yeah, this one university, do I put my home university or do I put the universities?
Here, home university.
University.
So if you are exchange.
Yes, yes.
Yeah.
Good morning. Yeah. So you told me to meet you in person.
You are here. Okay. Then we can talk afterwards. Okay. Your email, the one you wrote email yesterday.
Yeah.
Talk to me after this class.
Okay.
所以我应该扫 ，Thank you。
有办法扫，不能扫的，扫不到是。
可是我那个位置有点刚刚扫不到，可能是那一条挡住了。
哦，真的吗？有权限吗？
有些人有
就是会被我朋友就
为什么
被说？
为什么？
不确定是有所交大的信箱吗？还是
哎，交到信箱，要手交到信箱。
因为我朋友就是进不去，所以那个我想问一下，对啊，老师就是
要有交大信箱是不是？
不确定，
还是吗？你进得去吗？
我那时候玩过来的，进不去，玩过来的，那交大信箱，
要交大信箱的。
好像要交大信箱，好像我现在这样走。
For the one，
所以要伸出。
那我设定一下，我要设定一下。First of all, I heard about that. You probably need to log in using your NYCU email, but just give me some time. So after all these questions, then I will try to open the asset for anyone. But at this moment, you can already, if you have NYCU mail, you can already use NYCU mail to access this form.
老师，那个就是已经有选上的学生，今天会点名吗？
今天可能还不会点名，怎么样？
哦，没关系，只是想让大家有思考到。
哦，应该是还好，今天应该是不会点名。
Do we still need to hand you do these, or is it everything through the?
I will write email first to the student who got me selected, and then you can come in the next week to read this one.
Right, thank you.
First one, fill the form. I already filled the form. Then you can collect no problem, but you can bring in the text. Yeah, okay. And by the way, you can get this also. Yeah, it's it's a new international student. So you guys can know talk to each other. And there's a son. Yes, yes. Ivan Kim. Yes, he's also the. You already know him. No. The international student. So this is already been with me. Yeah. So you might be make a little bit connection. And if you have any question, you can always Ivan. Yes.
OK， 老师，毕业什么意思？好，
我看一下，不是，可以吗？要用 NYCU 这种，我看一下。
那些学生没有扫到那个脸书的，所以说可以。
没关系，先扫这个好了。对，等一下我觉得，因为这个可能比较多，我先处理一下这个问题。嗯哼，请说。
就是那个这个表单填完之后，是大概会什么时候知道？
哦，这2天我就跟大家讲，对。
哎，老师如果没选到的话，是不是要加钱？
对，说下还要，到时候还要拿那个单子来给我签。
OK，
对。哎，先填这个，填完之后我再会教大家。对，有选上我会再通知 email 通知大家。对，然后大家再下礼拜拿这个表单给我签。我们先填完这表单之后，我会再 make the selection。对，然后再通 email 通大家，然后这样的话下班再来。 是
不好意思，因为我刚才那个问卷没有填好
哦，那你再填一次。
啊，因为我已经缴交了，但是我
等一下，我看一下，为什么？我看一下，我要怎么 set？你现在还是没办法吗？
现在啊，
对吧？还是没办法
是。来吧。
哎，可是为什么我看一下，
可是这个 QR code 是不是会更新？它应该，假如说有新表单的话，
可是我只是把它开权限而已，但是我现在。我现在不太确定为什么他这没有办法让我开权限，看起来都是一定要 NYCU 不行。你可以进去吗？老师，
可能老师要设定一下。
可是你知道哪边设定吗？为什么我这边没有看到那个？
没有看到他说要设定。
对啊，没有看到有任何。对啊。哦，有看到。
哦，有限制教导。
对，我看到。
哦，好像有了。
有吗？我关掉。
试试看。
对，我把它关掉。
好。现在了吗？
已经有，应该是。
更新吗？
我看一下。
我试试看。
对，我把它有了，我看。
那我去外面，我这边网。
For the one who doesn't have the NYCU or probably from our university, now I think the access can be, you can access for the any email you have.
加速课程需要钱吗？
加入课程的话，就是先填在表单，然后把那个不用。你是哪个学校的？哦，那也是中央。
line right?
Yes.
To check about this. Because of trend line analysis. Are we talking about trend line analysis? Means you're doing
Yes, but you mean the Excel, there's some trend line, but there's some basic equation,
Yes,
but sometimes we will use more complicated. Yeah, but that's one example for trend line, so you can use that.
So for statistics software, you're talking about MATLAB? Are we looking at MATLAB? Are we looking at...
Well, it depends. Sometimes they use a different software. Sometimes use a Python. Yeah, that's also doable. As long as you can do the extrapolation. So it's all even for origin. You know origin? Yeah, origin. You can also add the equation there. So yeah, that's good.
So anything that can tabulate so-called a system line system out.
Yeah.
So for the model itself, then you will be mainly covering ESD or automotive, or are we looking at?
We will talk about the basic, and others for the very specific. Yeah.
Because within sustainability,
Wait, what year?
year 4.
Four. Your last year in the NUS?
Yes.
Oh, okay.
Specializing in sustainable electrical.
Oh, okay.
We are looking at semiconductors in terms of EVs.
Oh, okay. How many NUS do now in this semester?
We have 6 of us, but there's only 1 E student. The rest are all.
You are from E or you're not from E? I think in the past, before the COVID, I remember, or during the COVID time, there's still some like a US student, but after COVID, probably a little bit stopped. But then now you can see you guys come back.
Because the school has some system that they didn't update the NCTU to.
Yeah, we used to know last year.
So because no one really know why it's NYCU, so the sample rate drops.
I'll come back.
We don't have to start from just this.
First one, you fill this one, I will make the selection, and then after I will inform student start selecting, and then you have to print out the add-on form.
Okay, thank you.
可以扫一下这个 QR code 吗？刚没扫到。没有啊，这些花谢老师。
Okay, so we just have a couple slides. I think we can finish the class earlier today. I just look at the sheet that you guys have informed, and you can automatically count the number here. So I'm surprised that in this room, so I think we already have the 40 students, and then right now it's more than 100 to sign. So in this room we can have more than 100 students. I'm a bit surprised, but I have to say sorry that it's definitely not possible to have more than 100 because we have a group presentation. So group presentation will take a quite long time. So that would be the pretty like the disaster for us if we have such a long of students. So actually I target for this class, although in the beginning I set for 40, but I already expect. But I didn't expect that many, but I probably will set around like the total 80, 70 to 80. So you have to something prepare your mind that you probably has around like half of you probably will not be selected, and then the basic select criteria is by considering the urgency for this course that can help your current work. So that means usually the graduate student definitely have the higher priority. They probably need to conduct some of the reliability soon for their thesis. But I will not say it's 100% true, but because some of you probably is not come from the engineering field, probably won't be selected. So, but still have the chance for the undergraduate and all of the international visit students here. But first I need to look up all the background and then information you have filled. So yeah, I will try the best. Okay, so let's back. So this is another example like how the industry people try to plan for their quality or reliability testing. So that's called the advanced product quality planning here. So the idea is probably very similar to previous things. So first one, we have the concept approval. So we come out with several concepts to think about what would be the concepts that can suitable for our targeting spec here, and then we have the approval for our concept. So after everyone inside the company, they all agree this concept, they will start to have the product design and development, and also they have the process design and development here. So once reached to this moment that we can have the first prototype of our product here, and therefore we have the some product and process validation. We have product and process validation, and afterwards, so we have the process design and development verification. And then we have this one is important before we launch our product here. That's a product and the process validation again. So that means after the prototype, we will do validation. But before the production, we will also do a product and process validation again. And finally, we will release our production, and we probably will see some feedback here. So the most important conclusion is that once we have a strong reliability understanding, can accelerate the product development here. So that's a key goal for this class. Is in the end, we need to utilize our knowledge in terms of reliability, but our goal is try to make our product better and also to accelerate the timing that the spend on the product development here. And there's one thing is very important. Before the production here, as you see, there's a product and process validation. Actually, we have one organization that who actually try to make the spec for every semiconductor device here. That's we generally call as a JDEC. So in the JDEC, this association, they actually make the different reliability testing. So therefore, we call this as a JDEC reliability testing. So inside the JDEC, they have the very clearly how we actually can qualify to validate our product here. So if you try to look at the JDEC, just Google JDEC, you will find this website. That's a very old organization that has been trying to standardize for the microelectronic reliability for a long time. So you can see JDEC, Global Standard for Microelectronics Industry. So that's very important. So actually, every time when we try to launch a product, we definitely need to first to look at the JDEC standard to see our product actually reach the JDEC state spec or not. So it's important to understand we have such a organization try to standardize microelectronic reliability. So this is a general page for the JDEC website. You can say there's some memory, mobile memory, and so on, so on. These are ESD, even for wide bandgap power device here. So that means they try to specify for each specific technology and what kind of standard inside. And if you look at for the committee here, there's all kinds of committee try to, from the academics, from the industry, try to standardize this general spec here. So you have a mechanical standardization, quality for solid state product, and so on, so on, for digital logic, for memory, for DRAM, and last one, for example, for the wide bandgap power device here. So basically, you can find all of the spec as in the website. If in the future you work on the product, you have to check the standards here, because that's the final testing before you release the product. So since I'm the guy working in the wide bandgap power device, so I use this wide bandgap semiconductor as an illustration, as an example, to let you know what actually the probably any like the standards inside. So in this page, they mention this is a wide bandgap power semiconductor, and they clearly mention gallium nitride and silicon carbide are most mature wide bandgap semiconductor material and offer immense potential for high performance, more compact, energy efficiency power system here. And then in their standard, I think what they are trying to do is, first one, reliability and qualification procedure. So they are not only standardize the spec, they also have to standardize how do we do the test. If you want to qualify the product and you want to compare your product with other competitors, you want to compare your product in the previous version of a product, for sure you need to have the standard procedure, and then this procedure has been already verified by the industry or academic experts here. So in this JDEC standard, they will list the standardized reliability test procedure and all of the data sheet, elements, and parameters. So if you want to buy the new component, for example, from the mouser, from the digit key, for sure you will check the data sheet because you want to know what kind of the typical performance for this product. So in the JDate, they also list the standardized for all the data sheet parameter and also the test and characterization methods here. So this page I copy paste a few years ago, so that's already a little bit old, but right now they still update, but it's fine. This is just an example. So you can see in the 2021, they start to make the several standards. For example, this is a wide bandgap power device that are published for the bias temperature instability of the silicon carbide MOS device. So that's why the bias temperature instability that's generally we call the BTI. So that's why in this class we have to talk about the bias temperature instability. If you look back to the other slide I have mentioned, there's a specific topic we will talk about. It's called the bias temperature instability. So it's not only me to say this is important. It's really industry people, they also consider this is one of the key issues in the silicon carbide power device here. So, but what is actually related about the BTI? Actually, the concept is not that difficult. It's already something we have learned. So this is just the first 2 hours of this class, but you probably already start to understand BTI because we already talked about. So BTI is actually just consider the threshold voltage versus the time. So in the previous slide, we have been mentioned, ideally, property of VTH can be stable with the time. But this is probably at one specific bias, for example, VG equal to 5 volt. But however, if we increase the gate voltage, like say VG at 10 volt, then we can start to see our threshold voltage increase. So now this threshold voltage instability is generally depends on first one, bias. So large bias, more degradation, more shift. I think that's a pretty can be understood. And second one, this degradation, this shift is also related to the temperature, right? So we can expect the different temperature. Usually the high temperature will accelerate degradation. So high temperature will have the large shift in the most of case, but not the 100%. But in anyhow, this threshold voltage shift is a bias dependent. It's a temperature dependent. So that's why we also call this threshold voltage instability as bias temperature instability. So now you can see, actually we spend the time in the first hour just to introduce what would be the degradation of threshold voltage. Actually, that's already related to the key reliability issues. Sometimes we just call the BTI, bias temperature instability. So now if you look at this website and you look at this information, probably you can say you're now familiar with, at least you know what is the BTI means here. The BTI is just related to the threshold voltage instability. And of course, inside this document, they release lots of documents, so they have say the new test method for the continuous switching, but that's for the gallium nitride. and so on and so on. So they try to release several documents, try to standardize all these testing methods. And if you have been in the field for a while, then probably you have already heard about the JDEC. And then, although the JDEC standard still is ongoing, making the new one, but we have some very typical JDEC that have been used for silicon for a while. So this is a typical JDEC based on the silicon technology. So we have several testing items need to be done before we claim our product is reliable. For example, the first one is called the TC. That's a temperature cycling. The purpose for doing the temperature cycling is because if you consider your semiconductor, I know probably 50% of you are pretty fresh, so you have not have enough understanding, but you can imagine the semiconductor is so complicated, so you not only have the substrate, you probably have a lot of dielectric, you have lots of material on top. In the end, you also have the packaging, you have the bonding, you have so on and so on. And the issue is that all this material will have what we call the temperature coefficient. That's we call the temperature relating expanding coefficient. So that means that once you put this material, your device in some relatively high temperature environment, you can expand all this, even for the metal line will start to expand because due to the temperature. That's a pretty normal, right? So during the high temperature, all the material will expanding. And during the low temperature, all the material will become smaller here. So that's related to the expansion. So therefore, we do the temperature cycling because we want to make sure that if we try to evaluate this expansion, it then won't cause any value for this product here. So usually we do the condition from -55 to 150. We do the 1,000 cycles, and we will check the parameter in the certain cycle. For example, 168 cycle, 500, and 1,000 here. And of course, we cannot test all of the product. So usually what we do is we would pick up the 3 lots. And then for each lot, we will take for the 77 device for the testing. So that's a temperature cycling. We have a H3 TRB. So H3 is H3, that means a high temperature. So we have the high temperature, high humidity, and high voltage. Also, we would stress the device for 1,000 hours and to make sure that's the device still functional and then the characteristic doesn't shift. And the most often used here is HTRB and HTGB here. So HTRB, the full name is high temperature reverse bias. So in this case, we will stress our device in the very high drain bias. So this is one example. You will stress the device in the high temperature 150 Celsius degree, but also at the very high drain bias. This is a VD. Another one very often used is a HTGB. And here we will stress the device at the very high gate bias. So these are the 2 most often used JDEC testing. But the issue why we have these standards, but why do we still have studied reliability? The issue is because this standard is based on very old silicon technologies. As you know, our technology is, the evolution for our technology is very fast. Every 2 or 3 years, we have come out with a new technology. So every time we need to redefine again the JDAC. But the problem is that before we redefine the JDAC, we need to first to understand the physics, why this testing methodology is suitable for the certain technology, because this testing is based on the value physics of one specific technology. So therefore, if we face a new technology, we have to first to understand the value physics, and then we come up with a new JDAC standard. So that's the entire whole society is continually working on, because every new technology has a different, slightly different value mechanism, and then we have to understand. After we understand, we have to define the new standards. Also, that's one example. If you're interested, you can look at this YouTube. So this is, when we talk about reliability, it's not only happen in the semiconductor fab. It's actually in all over the industry, even for the product industry. So this is one example in the Amazon Lab 126. So you know the Amazon has a very famous product. For example, the Kindle is like the pad, the e-book pad. But they also have to do the lots of reliability testing to make sure that the product you have can be survive for several years, can be even survive for a certain extreme condition. So it's interesting to look at this video to look at how actually industry try to put these things in series, especially in terms of reliability aspect. Okay, so the second goal for this course is, first one, you have to understand no reliability is equal to no business. So that's why if we want to have the good customer trust, we want to launch a product that can have the very good business in the market. The first thing, not only for good performance, but also we have to make sure we have a good reliability as well. And especially the new technology based on the advanced design and novel material. For example, like the FinFET. Although FinFET is not a new technology anymore, it has been come out since 2000, but still we do the lots of the scaling in the FinFET, we do the stacking, we do the new gate stack, we reduce the pitch. That actually will create some additional reliability issues. So there are still lots of people working on the FinFET reliability. And also for the high K dielectric, we have so many new material for high K. Traditional, we use a hafnium oxide, aluminum oxide, but now we have the zirconium oxide, we have lots of new material. And these all new material will all suffer the new reliability issue. Of course, like a wide bandgap device. So wide bandgap device is very suitable for the power and the RF application. And then the things for the wide bandgap is that usually they are not growing on the same epitaxy, or their process is relatively complicated. They probably need a high temperature annealing. They have a different aging, and also the wide bandgap we expect to operate in a higher voltage. So once we operate in a high voltage, we can expect the reliability things can be worse as well. And also, for example, recently very hot topic for the ferroelectric. So that's mainly used for the memory and also for the logic device. But the thing for the ferroelectric is that the material is sometimes not very stable, and therefore lots of reliability issue can come out. And also we have the 2D material that's mainly used for the logic device. These all cannot be commercialized if there's no proven reliability. So first we need to prove that the reliability can be achieved in a certain level. Otherwise, all this material, all this device shows it's a very promising, very attractive performance. But if they don't have a good reliability, it's useless. Okay, so therefore, a good engineer should recognize, first one, the statistical and characterization method. So in this class, we will teach you how to do the user statistic, because as you see, actually the manufacturer, they try to make the product thousands of wafer daily base, but for sure you cannot test all of them, and you can only test a small amount of the device to make sure they have a good reliability. On the other hand, you cannot test for the 10 years. You can only test for 3,000 hours. That's already the maximum. So how do we use a small amount of data to predict the whole device behavior? That's why we need to have the statistic. That's why we learn the statistic from high school, right? So we can use a small amount of data set, start to do the analysis to predict the overall group behavior. So that's why we need to use a statistic tool. And second one, identify the reliability issues. Yeah, we should also be aware that every semiconductor technology always has a reliability issue. So we need to be aware of that, and then we have to accept that, and then in the end we try to address that. And then also try to evaluate the failure phases here. That's also important. So we understand there is a reliability issue, but now we have to understand what kind of phases can lead to this reliability. And also, the last important is we have to design the reliability. So as I say, the goal is always improve the reliability. So we need to come out with a certain, no matter for process design, material design, device design, layout design, testing design, whatever, or circuit design. But in the end is we need to achieve the good stability. So in this class, for sure, we will talk about the basic semiconductor device process, but also one of the key is a statistic tool, because you will not learn this. Many of you probably, if you start working on reliability, you will get confused as to why we need to use a Gaussian distribution, we need to use a Weibull distribution, we need to use a log normal distribution, why we need to consider certain statistic normal distribution, and so on and so on. Because these statistics help us to use a small amount of data set, but we can understand the whole group of the characteristics here. And characterization method for reliability evaluation will be also covered in this class here. So this 1, 2, 3, 4, 1, 2, 3, 4. That's actually the learning outcome for this course. So that means by the end of this class, you should be able to understand these things. Okay, so as I say, we will start to talk about some important reliability issues here. And in this class, we will cover the 4 most important ones. These 4 actually is already enough. So some of the people actually they work on one of them for whole their life, from like my previous professor when I was at IMEC. Actually, he works on the BTI and TDDB in silicon for his whole life. And some people work on the ESD for whole life, and some people working on the electron migration for his whole life. So actually, each one can be the endless research and understanding, because the technology is keeping coming with a new material and new spec, and therefore this reliability issue will be come out again. But the good thing is that we all can learn from the past. So in this class, we use a typical silicon-based MOSFET to understand this reliability issue. And this experience can help us to understand the degradation that happen in the new semiconductor material and device. So the first one we will talk about is a bias temperature instability and interface trap. So generally we call this as a BTI here. So then we have to use a MOSFET as a one example. So that's a second time for you guys. If you are pretty fresh, then it will be the second time for you guys to understand the MOSFET. But in the end, even you are still following, you can already have the good basic concept for MOSFET, because we will use the MOSFET again to understand. So MOSFET is a structure where we have a substrate in the bottom. In the left-hand side, we have a source. In the right-hand side, we have the drain. And then on top of the chain, this region, we have a dielectric. And usually we use the silicon dioxide. That's the most common one. And then on top of the silicon dioxide, we have the gate metal. So that's the very basic structure for MOSFET. And as I said before, when we try to operate MOSFET, first one, we will put the source as a grounding. That's the most of the case. We apply the drain bias with a positive, and then we apply the gate bias. So the concept for the MOSFET operation that has been already mentioned before. So that's actually, once we apply the gate bias, once the gate voltage is high enough, we can certainly induce the electron in the channel. This is a channel. So we will have the electrons here. So that's our electron. And usually we call this as a channel. And because we apply the drain bias in the drain side, so the drain bias will start to attract electrons. So your electron will start to move from the left to the right and become the drain current. So that's the idea of this the MOSFET operation. So now, again, if you look at for the IDVG curve that we have been already mentioned. So now we all understand. First, with a small bias, it should be there's no current because the carrier in the channel is not high enough. But beyond certain bias, we can start to expect the current is increased. So typical IDVG curve is look like in this way. And we can define this one as a VTH1 here. And then once we apply the positive bias, for a while here, we often see the curve is changed, like in this way. So we get a new threshold voltage, but threshold voltage is become larger, and also the current is degrade. And the difference between this and this, that's we call the delta VTH, and sometimes we also call this as a hysteresis. And this delta VTH is correlated with first one, bias, and second one is a temperature. So that's why we call this as a bias, temperature instability. And because right now we consider the case of given a positive bias. So therefore, to be more specific for this case, we also call this as a PBTI. Because right now we apply the positive gate bias. So that's why we call this as a PBTI here. Since we have PBTI, that means we also possibly has a NBTI. That means we will see the negative, we apply negative gate bias, and then we will see the negative shift. This will be happen in the case of the P MOSFET. But now we have to mention again, this is a case of N MOSFET. So the N means the carrier, the carriers in the channel is electron. That's why we call this as an N MOSFET. So in the N MOSFET, the majority carrier is electron. The reason to induce the current is the electron. So you can see it's because all these electrons, that's why we have the current. That's why we have the current here. So that's why we call this as an N MOSFET. But on the other hand, we also have the case what we call the P MOSFET. But here we won't draw the P MOSFET again. In the future, we will have some explanation later. But the P MOSFET has just a completely opposite direction of the IV compared to N MOSFET. So it's also very simple. First one, you apply the negative gate bias. With enough negative bias, you start to have the current here. So you have to apply the negative VG here. And because you apply negative VG here, sometimes, not always, but sometimes you will see your threshold voltage shift in the negative way. And because this is applied for negative to induce the BTI, so that's why we call this as a NBTI. And the reason, not always, but the part of the reason that can contribute for this threshold voltage, either for PBTI or NDTI, this is mainly because we have the lots of the traps. We have a lot of the traps between the dielectric and then semiconductor. In this interface, we have a lot of the traps. Sometimes we just call this as the interface traps. The basic idea why we have the traps here is because of these are the two materials. This one is semiconductor. This one is dielectric. Anyhow, just another material. So basically, if you put the two materials side by side together, you can imagine there's always something happen in the interface region. Of course, in here we have more some more academic way to explain, but the basic understanding is that you put the two things side by side together, you can imagine in this interface, it's possibly you can have something happen. In here, it's called the traps here. The traps, it means that it's something that will try to capture. So the traps, it's a semiconductor, that's what we call the 缺陷. But actually, in reality, you can always, the trap or trapping is always a term you can use in your daily life. That's an English term you can use in daily life. Sometimes I say that, for example, you have been working with homework for months, several months, you still haven't finished a project. You can say, I'm trapping in this project. I'm trapping by this project, because that means 你被这个计划 trap 住、困住. So that's also the term you can use in the English life. So don't have to really think about this purely like the semiconductor words. But if you try to look at some of the daily life example, you will figure out that actually this trapping was original created for the daily communication, but later people feel like this also can be used in semiconductor, so that's why they use the interface trap. But the trapping is also the one that you can be used for the daily communication as well. So the traps, basically the function for the trap to capture some carrier. In this case, we consider the electron. Of course, you can capture the holes here. So it depends on what kind of the trap. So it can be electron or holes. That depends. So we will talk about the different traps later. So first, that's for the BTI. The second one is my favorite one. That's a TDB. So I was, as you know, all this topic has been working by the several people. Some people, they actually working in his whole life. So TDB is actually the major part for my PhD thesis. So I've been working in the TDB since I was a student. When the first time is working on the gallium nitride. So at the moment I start. But nowadays, I still working in TDB. I think some of you in this classroom are my students. So they know we are still working in the TDB. So the good thing for this reliability knowledge is that you learn once, you can apply for your whole lifetime. That's a pretty good advantage, right? You don't have to keep learning new. But the problem for the new device technology, you have to keep learning new. So now you have a FinFET, you have a nanosheet, you have a CFET, you have a 2D. After 2D, you have so many different material for 2D. You have so many material for ferroelectric. But for TDB, they always accept. They always accept phenomena. So it's always good to learn these very old, but that can last forever knowledge. Okay, so the second one is a time-dependent dielectric. So as I say, one of the key consideration for reliability is a time-dependent characteristic. So therefore, we have to consider they can have the time-dependent dielectric breakdown here. So the time-dependent dielectric breakdown is, again, we will first to draw the MOSFET to explain. So we have now I can draw faster because I believe you guys should quite familiar with the MOSFET. So we have a gate region. So this is a gate region. And then what we usually do, as I say, for the MOSFET, we always apply, most of the case, VD at 1 volt here. But at the meantime, we also will apply the gate voltage here. And then we will start to induce the electrons here. The electron will be flowed to the right-hand side and become the drain current here. But something we don't talk so far is related to the silicon dioxide. So ideal oxide is a perfect insulator. So what's a basic definition for insulator? From high school, we already know. Insulator means that it's a material that supports there's no leakage current. There's no possible to have a carrier inside this material. So that's why we call this as an insulator. So ideal perfect insulator, that means no leakage current. So that means actually we apply the gate voltage. In the previous case, we only consider we apply gate voltage, but we apply a drain, but the carrier can be flow to the right. But have you ever thought about, since we actually apply the gate, the carrier, this is negative charge. So negative charge should also possibly flow towards the top, right? Because you have the positive gate bias on top. So certainly you have some electron will be trying to attract toward the top side here. So, but ideally, there's no leakage current. So that means the IG should be very small or nothing, or we cannot measure anything of our gate leakage current. But if you try to use your semiconductor measurement machine, try to measure the previous, we are only focused on the IDVG, but now we look at for the IGVG. You can actually always sense the gate leakage current. Although it can be very small, it depends on how good your dielectric is or how large your bias is, but you always can sense a small amount of the gate leakage current. So that means actually, although it is a perfect insulator, but how come we can still have leakage current go through? So that's why we need to start to come out with quantum physics here. But if you talk about quantum physics, first we need to understand what is classical physics. So if you back to the classical physics, that's how Newton told us, if you have the wall, you try to throw the ball against, I think in this classroom there are many of you from the physics department probably have the better physics than I have. But it's fine. For the quantum physics, it's not that difficult. We don't need so complicated. We just need this basic concept. So in the case of a classical physics, if you throw the ball against a wall, there's only one possibility can happen. So that means you can see the reflection of this ball. You can see the ball bounce back to you. So that's how Newton told us. This is how classical physics. But now, if you look at this case in the semiconductor world, still the same. You apply the gate bias here. You actually attract the carrier from the bottom to the top. So ideally, all these carriers should be bounced back, and you won't be able to sense any leakage current. So therefore, we found out that classical physics might not be true in the case of the semiconductor world here. So that's why we come up with another quantum physics. And the conclusions of quantum physics is just try to help us to explain these phenomena. So again, we have the wall here. So now we still throw the ball. Of course, now it's not real ball, it's just a carriers. So the carriers can be electron, can be hole. of course, the first scenario can be there's some part of carrier will be bounced back. So that's still true. These still follow the classical physics. But another thing is happened. You found out that certain of the carrier can penetrate into the wall and reach to the another side. Of course, this cannot be explained by the classical physics. This can be only explained by the quantum physics. And this phenomenon is what we call the tunneling. So the tunneling means we apply the gate bias here. The carrier can certainly penetrate across this dielectric and reach in the other side and become our leakage current. So this will become our leakage current. So that's why finally we have the physics that can help to explain why it is possible to have the gate leakage current, why we will always sense the leak current, even less a dielectric, no matter how thick your dielectric can be, 50 nanometer, 100 nanometer, you always can sense the leak current as long as you give enough bias here. So that's because of the quantum physics, the quantum mechanism here. So this is how we learn from the semiconductor physics. And of course, the quantum mechanics is pretty complicated. You can learn from whole semester, even for whole life. But from the semiconductor point of view, I think this is what we really need to know. And then of course, there's some part of the equation, but I think that's enough. It's mainly the physics of the mechanism is help us to understand the phenomenon. It's not help to confuse. So it's important to know that these are help to understand, not rather to confuse us. So you can see, because of a quantum physics, because of tunneling, we start to see the gate current. So finally, we can expect there's a part of a gate current can be sensed from the gate side. But however, this is IG versus VG. That means this is time independent. But however, if we try to put the time dependency here, there's another interesting observation can be found. So we put the IG versus the time. And at this moment, you try to bias with a certain constant gate voltage. Then you can start to see the curve is not flat anymore. There's a certain goes up and down, and that actually indicates some of the physics here. In most of the case, we will see, first one, you will see the current decrease. After a certain moment, you will see the noisy happen. And if time is longer enough, you will see the current increase. So this is not the measurement error. This is not the error information come from the semiconductor machine. It's actually the physics, some physics change inside our device in the end to leading to this phenomenon. And generally, the current decrease is because we have a trapping effect. Of course, this is just the first class for introduction. I will not explain why there's a trapping here. But just for your information, every curve, whatever you measure, there's always something happen. It's not just the measurement error. So you have the trapping, and why there's a noisy, of course, there's still physics here. It's what we call the soft breakdown. And why there's a current start to shooting, that means a hard breakdown. Okay, so generally that's a 3-phase for our TDDB phenomenon. For sure, if you have a different dielectric thickness, you will see the different characteristic, but most of the case, we will face these issues. Okay, I think it's enough for today. So probably after this class, you can consider you will leave or you will keep staying for this selection, this class. And we'll make I will email to the one who got selected with a few days, and then you can bring me the A-down sheet to me, and I will sign in the next week. In the meantime, if you have any questions, just feel free to let me know. So we will stop the class here and see you guys next week.